Thank you, Martin. Okay, good evening. So today I'm going to be talking to you about the tides. In particular, I'm going to be putting some emphasis on what I term tidal stream rather than tidal range, but don't worry, I will explain the difference between the two as we go through the talk. So I'm going to start by outlining a little bit about what causes the tides, what sort of characteristics they have in terms of a moving body of water, and perhaps how that compares to some of the other forms of renewable energy that we have. And then the majority of the talk, I'm going to talk to you about technology types that exist at the moment, that are in development, in terms of some of the engineering decisions that go behind them, and the importance of that technology that we take forwards. Finishing off, talking a little bit about some of the work that we've been doing at the university in terms of tidal energy research. So what causes the tides? Primarily, the tides are caused by the movement of the planets. Primarily, the lunar component by the moon is the most significant, and it's the gravitational field that we get from the moon that pulls the water on the Earth, the sea, towards it. On the sort of opposite side of the Earth, where we get a less gravitational effect from the pull of the moon, we also get an opposing bulge occurring, simply that there's less gravity pulling that water down towards the Earth. So as the moon rotates around the Earth, similarly it pulls the tides around the planet. Added complication from that is that the secondary component from the sun, the solar component, also has a contribution to make in terms of the tides and the variation that we get on a regular basis. Essentially, when we see the moon and the sun at perpendicular angles to each other, we have what's recalled as the Neap tidal cycle. Whereas when they're in alignment, either with the moon on the far side or the moon in a sort of eclipse mode, in line together, we have the spring tidal cycle. So you can see that we get a greater gravitational pull when things are in alignment compared to when they're out of alignment. Okay, there are other planets within our solar system. They all have a contribution to pay, but essentially they form less than 1/1000th of a difference compared to the solar component. So we won't go any further than explaining it, other than the two planet system that we have at the moment. Now, with respect to the planets, relevant to their cycles, we get the time cycles of our tides. Typically, we get 2 diurnal tides per day, so the tide comes in and out twice per day, every 12 hours and 25 minutes. On top of that, we get a monthly cycle associated with the alignment of the sun and the moon. That gives us our Neap spring cycle. Then on top of that, we have other alternatives in terms of the lean that the Earth has relative to the moon, and that can also cause differences. Now, it's important to realise that today I'm talking about tidal energy in terms of flowing water. I'm not talking about tidal currents. Okay, tidal currents are completely different. They exist on our oceans and are moving 24 hours a day, 365 days a year. They don't oscillate, and essentially they're due to rotation and also due to the thermal effects that we get within the oceans. Warm water moving north from the tropics, the Gulf Stream, coming back down again, the North Atlantic conveyor, and then across again in the tropical areas. So yes, they are very valuable in terms of potentially extracting power from them. The difficulty is that we can't switch them off. So in terms of putting a device in and taking it out again to do maintenance, it becomes very difficult because you'd constantly be battling against the ocean current. So the good thing about the tides is because they vary, they do have periods of slack water. It does allow us to do some maintenance and some work on the devices. So I mentioned an important word at the top there, predictable. Okay, most forms of energy in terms of renewables, we don't know quite when the wind is going to blow. We don't know when the sun is going to come out. But we do know, because of the movement of the planets, that we can predict the tidal flows, and reasonably accurately. So this is an extract from Hisham in terms of data, with the red line, the predicted flow in and out on the 19th and 20th of January 2005, and the blue is the actual performance of the tides measured during that period. I'm going to take that as being a spurious data reading. The tide didn't suddenly rush out and come back in again. But you may note that we've got a slight variation here, particularly on the evening of the 19th and the morning of the 20th. Is there any guess as to what that might be caused by? Okay, very good. So atmospheric conditions at the time, and prevailing wind direction, the wind can lead to, in this case, almost half a metre or so additional height in terms of the tidal range, and that can have a significant impact when you're designing coastal defences, etc. It can also have an impact when you're designing tidal energy devices. Looking at longer term, a month scale in this time, we can actually see the variation caused in terms of this Neap spring cycle of the alteration in the tides, that typically during the Neap period we have about half the tidal range to what we have during the spring cycle. So we've outlined what tidal range is in terms of variation in height as the tides come in and out. We haven't really talked much about tidal stream and how that matches to it. So tidal stream, when I refer to tidal stream, we're talking about the velocity of the moving water, whereas tidal range, I'm talking about the height of moving water. There's a nice direct relationship between the two, that typically, as you'd expect, if you get greater height variation occurring, you get, similarly, the water's got to move in and out a lot faster, so you get a similar increase in terms of the velocity of the moving water as well. So from that data that we've had in terms of range, we can map that directly to tidal stream and variations in speed of flow as well. Other things to be aware of, that the water isn't moving as one body. We do get significant effects in terms of friction from the seabed, and depending on where you are on the coastline, what the local bathymetry is, whether you're moving around a headland, whether you're in open ocean, whether you're in a deeper estuary, will depend on what the flow speed is relative to depth. And this can have a significant impact if we're putting things in the water and they vary during the height of the water column. The loads that they experience as they go between the top of the water column and the lower part of the water column can be significant. So we have to design around that. Similarly, they're not nice moving bodies of linear flow. They are very turbulent. We've got some data here sampled at a higher frequency in terms of the movement of the water, and there's quite a lot of, in effect, noise within the cycle just due to the turbulence of how that water is flowing. Fortunately, because the rotational speeds of most devices are quite slow, this immediate turbulence effect isn't going to have such an effect on the power output from the device. Okay, so we get a more uniform flow of power output because the rotational speeds of the devices remain relatively uniform despite the turbulent conditions that we put them in. Globally, how the tidal energy is distributed, well, this is looking at the seabed frictional effects. You can see around the sort of Australian coast, around sort of China, Japan area, there's quite significant amounts. Over in Canada, they also have a significant tidal range. In the UK, the very far right-hand side there, just on the boundary, is also blessed with significant tidal resource. Several metres. I think we have the second highest tides in the world around our coastline. Looking at it, zooming in on the UK, this is one of the DTI Atlas maps that's been produced. Although this is a snapshot in 2004, they have been updated more recently since, and there's an online application that you can use to find out and discover what the tidal conditions are like closer in your region. Generally, in terms of the spring tidal flow, we're looking at tidal currents in excess of 4 metres per second. Okay. Anything probably greater than 2 metres per second is seen as very lucrative in terms of the economical benefit and the extractability of that resource. We zoom in on the sort of northwest region, we get a bit better indication that there's a significant resource here around Anglesey, a little bit to the north of the Isle of Man. There's even within the Morecambe Bay area a significant tidal speeds that could be extracted in terms of getting the kinetic energy out of that flow and converting it to electrical energy. Now, when it comes to calculating how much resource there is, there's a lot of variation in the answers that you'll get. It seems that no one is willing to put forward an ultimate answer in terms of what the resource is, and partly due to the way that it may be calculated. So first of all, if we consider the flow in terms of kinetic energy. Now, most people should be familiar with kinetic energy, the equation of a half mv squared. A half times the mass times the velocity squared is the kinetic energy of a moving object. The mass in this case is a moving body of water, and if we were to take the swept area of the turbine, multiply it by a set length in terms of the volume, and multiply that by the density of that fluid, we get the mass. In terms of the length of that, if we treat how it's going or moving in 1 second, we get a velocity component. So it turns out, in effect, the kinetic energy in the flow can be related to a half rho AV cubed, where rho is the density, A is the cross-section of our turbine, and V is the water velocity. So if we double our water velocity between the spring and Neap cycle, potentially there's up to 8 times the power available to be captured. Unfortunately, there's an alternative method of treating the tides as a tidal wave. Okay, and the tide is a wave, it moves around in our oceans, it's just that it happens on such a time scale that we don't consider it to be a wave. But it goes up and down just like a wave, it's just that it takes several hours for it to go up and down and for us to realise that. And the wave is actually moving very fast, it's about 80 miles an hour that the wavefront is actually moving around our coastline, so it is significant. If we apply the equation in terms of wave power, we have a v squared relationship. So with this spring Neap cycle, rather than being 8 times variation, we've got 4 times variation. A third argument is based on the seabed friction that we get from the tides, that as water moves over the seabed, it dissipates a certain amount of energy due to the friction effect of the seabed conditions. If we start extracting energy out, or kinetic energy out from the flow, there's less to be dissipated on the seabed, so potentially we can extract more than we thought we could without damaging the local environment. Okay, so, but what friction factor do you use? It depends what the seabed is, whether you've got weeds, whether you've got debris, whether you've got rock faces. All sorts of factors could go into that particular calculation. So what I think is important, that any potential location for the type of technologies that we're looking at, you need to make sure that there's an appropriate site survey done beforehand, so you understand the tidal flow, you understand the conditions, you therefore get a realistic estimate of the potential power capture available. But let's put this into some of the experts and see what they've come up with in terms of resource. It varies. The most recent one here, Committee on Climate Change 2011, they're hedging their bets anything between 18 to 200 terawatt hours. Okay, I imagine it's probably certainly the 60-70 terawatt hours available relatively easily. Getting up to the 200 terawatt hours, I imagine, would be slightly more difficult. Okay, but needless to say, it's very large. Just to give a figure for how large, if we assume a channel, uniform channel in this case, 0.5 kilometre wide, 50 metres deep, and the flow speed essentially going across the bottom here. Typically, once we get to about 3 metres per second, in that channel, there would be sufficient energy to power a city roughly the size of Edinburgh. Edinburgh is about 220, 240,000 homes, I think. Okay, so that's just from one channel. If we extracted all that energy, it could power a city the size of Edinburgh. In terms of the economics, it's no good just having lots of power if we can't extract it economically. So looking at some of this, typical cost estimates back in 2006 put tidal energy in the 12 to 15 pence per kilowatt hour bracket. Okay, as we install more, we get savings in terms of mass manufacture, improvements in terms of installation procedures, reduced maintenance requirements. That price is predicted to cost to potentially below 5 pence per kilowatt hour at the 1.5 gigawatt installation point. Similarly, the more recent report in 2011 was suggesting somewhere between 9 to 20 pence. Those that have looked at the news recently will realise that the agreed strike price for the new nuclear facility is somewhere about 9.5 pence per kilowatt hour. So on that basis, at a reasonable effect, we're not far off competing in terms of nuclear energy and nuclear power. Does anyone know how much they pay for electricity at the moment? Too much. I would argue the opposite, actually, but 14.32 pence is the typical EDF tariff for the northwest region as of yesterday. So you can see that the distribution cost, the maintenance cost of the network, actually getting it to you, all adds additional cost, plus the profit from our suppliers. So even though we might be supplying it at 9 pence, we're still within the sale price in terms of 14 pence. And that figure is only ever going to go upwards. CO2 emissions are all important in terms of trying to compare technologies. We can go nuclear, we can go gas, we can do recycled initiatives. How do they compare in terms of the emissions requirements? Well, tidal energy, based on the CGen device, which we'll talk about in a few minutes, it comes in at the lowest at 15 grams of CO2 per kilowatt hour of capacity. Nuclear comes in just slightly above that at 16, and then you can see that the coal and gas are significant in terms of their outputs and pollution. Typically they would be about half that figure if we had the sort of district heating systems powered by the power stations as well. Okay, but still significantly higher than what we have. However, I'm not suggesting we compare those figures like with like. They're from a variety of sources, and it depends how far the calculation has gone in terms of the end of life recycling of these power plants. I don't think anyone's really worked out yet in terms of nuclear power what the recycling cost is, returning the land to what it was originally. So tidal turbines, what do they look like? Well, in terms of tidal stream devices, which I'm going to talk about in a moment, they're sort of this size compared to the wind turbines that most of us are familiar with, about this size. So that's a scale drawing. Typically 60 metres diameter for the wind turbine against 18 metres diameter. That also depends on the flow condition, so it depends how windy it is or what tidal stream velocity you've got as to the actual size of those rotors. The CGen device is only 16 metres and it's a 1.2 megawatt machine, so it just depends on the conditions. Also important to realise that 1 megawatt is now quite old. Typically the offshore systems are now looking up to 5/6 megawatts in terms of the size of machine, so they have a rotor diameter in excess of 120 metres. So I would expect tidal devices to go similarly up to perhaps a 30 metre diameter sometime in the near future. So now we've covered the resource and we've talked a little bit about how it fits in against other technologies. Let's have a look at some of the devices themselves in terms of being able to extract power and some of the things that we can pick out from them. Now, if I was to go and Google tidal energy device or tidal stream energy device, there's a number of hits that I would get. I think the EMEC website lists over 88 device types. I'm not going to cover all of them today. I'm just going to pick out and highlight a few in terms of what I see as being significant and how the technology is moving forwards to potentially give us a solution to what we're searching for. So the first one I'm going to cover, just because when I mention the word tidal, most people think of barrages. Just to talk briefly how barrages fit in with the equation. Probably the most famous of which is Lance over in France. 24 10 megawatt hydro turbines installed. You build it across an estuary, it stops the flow coming out, and you have a number of turbines then that let the flow through, and that allows you to generate the power as you get the difference in height or range. So barrages are a tidal range device. The largest system in the world is now in South Korea, 254 megawatts compared to the 240 megawatts of Lance, which has been running reliably since the 60s. In the UK, there's been a lot of talk in the media about a 7 barrage. It was done on a feasibility study again by the government in 2008. It's since been rejected by the coalition in 2011 as being too expensive. But to give you an idea of the size and capacity of the sort of main route, which was the 7 Cardiff Weston barrage, you're looking at 214 40 megawatt turbines. So not the 40 10 megawatt turbines, 214 40 watt, 8.5 gigawatts potential peak output. That's more than 3 nuclear power stations. Okay, 19 billion for a nuclear power station, 30 billion for a barrage. But barrages, they stop the flow, they can be damaging to the environment. What other alternatives are there? Looking at tidal range devices, one idea put forward or proposal put forward is that of a tidal pool or lagoon, where rather than building across the estuary, you build just within a proportion of it, and you use that man-made pool then to actually fill with water, and again as the water goes in and out, you generate power. An added advantage of the tidal pool is if you start dividing it up into smaller pools, you can start generating power not only when the tide is coming in and out, but if you stagger when you open the gates between the different pools, you can generate power for a significantly longer period of time. Okay, so that's sort of shown here with the 3 pools. Essentially you see oscillating, so the power output we get at the top is more consistent and you're getting power over a longer period. There has been proposals put forward, again within the Severn Estuary, in terms of Cardiff Bay, a proposal of a 60 megawatt, I should say, 5 kilometre tidal wall. I think one of the advantages that no one's really looked at yet in detail for these lagoons is the potential for energy storage. Okay, you could build the wall a few metres higher, you get half of it filled for free, the rest of it you use in terms of wind, solar, other intermittent sources to pump the water in, and then it's available to extract when you want and how you want, just because it's a big tank of water and you just empty it out when you need the power. But as said, barrages, they're seen as being damaging. They require large civil infrastructure, large capital outlay at the start, and you're not going to get a return for 10, 12 years down the line. They also displace habitat of wildlife. Silting, potentially of estuaries, would require maintenance. They change the habitat, I would suggest, rather than damaging it. Cyril Perry at EDF France says of Laurence, a rich and diverse habitat for wildlife. Okay, so wildlife is adapted to the infrastructure, it's adapted to the new tidal range that it sees, and there's no reason to think that it wouldn't do otherwise. So rather than build a barrage, very expensive, let's look at tidal stream using the water velocity rather than the water height as an energy alternative. So much smaller in terms of construction, much cheaper, therefore for one-off devices, much quicker return on investment in terms of the economic value of it. Potentially they can be completely submerged under the water, so it doesn't need to interfere with shipping, it doesn't need to be visually unattractive. And the channels are left open, so you're not disrupting shipping or anything else. To give a balanced talk, however, I should perhaps mention some of the disadvantages. It's not a win-win-win. We still have to be aware that although the tide is predictable, it is still intermittent. You know, we get periods of high tide and low tide, and at those periods we have slack water when the tide isn't moving, and when the tide isn't moving, we're not able to generate power. Fortunately, the time where the tide comes in and out around the UK coastline is at different times, and therefore by having a series spread around the coastline, we are able to a certain extent to neglect the intermittency by having power generated at different points. And we also have this problem still of the Neap spring cycle, so although we might build machines for a set capacity and value, they're only really going to be performing at that half of the time. The rest of the time they're only going to be performing at perhaps a quarter or an eighth of the potential power that could be there. So some of the device types themselves, in terms of tidal stream, this is one of the earlier devices, the Stingray by Engineering Business. They made a prototype system that they deployed off Shetland. Essentially it consists of a hydrofoil, essentially a wing, similar to what you'd find on an aircraft, on an arm. As the tidal flow flows over the wing, it generates lift. That causes the arm to go up. It then pumps hydraulic fluid down through that. That pressurised hydraulic fluid is then used to generate the electricity. So it essentially oscillates up and down, a bit like a fan, using the water flow to let it oscillate up and down. In terms of how they'd be on the seabed, the sort of artistic impression here, where you'd have several of them in a farm or an array arrangement, all oscillating up and down like the nodding oil wells, I guess, that you see in Texas, all generating power. Unfortunately, Engineering Business, after the Stingray prototype was deployed, although it was tested and they saw it as being potentially economic at 6.7 pence per kilowatt hour, they then withdrew from the market at that time. Essentially the government, in terms of its funding mechanisms it had in place for tidal energy developers, suddenly put a hold on things, and therefore they didn't see any point in being the first people in the water, doing all the development, hosting all those costs without any support from government. One of the downfalls of the Stingray is that due to the oscillation of you going up and down in the water, as you go to the downstroke, you get into this shallow water where you have the frictional effect of the seabed. So your water velocities are a lot lower, and therefore actually getting the thing to come back up again into the high-speed water up at the top is quite difficult. So to get around that, Pulse Tidal, in effect, have taken the same concept, except they've made a seesaw arrangement. So connecting the two blades, we essentially have an arm link, and that acts as a seesaw. So when one arm is up in the strong currents, the other one is down, and therefore there's potentially plenty of power there in order to get it to oscillate and able to work in the free stream. They've had the 100 kilowatt prototype installed in the River Humber since 2008, and they've got a potential planning going in place for Lynmouth, Devon, for a new commercial prototype. The big advantage that they see over other manufacturers is the fact that they oscillate up and down. They scribe, in effect, a rectangular area in terms of the water surface. So in a shallow estuary, where perhaps you're limited by the seabed and the height of water, you're able to capture significantly more of the energy from that, rather than just scribing circles and having a lot of waste in between them. Probably the leading company in terms of technology development is Marine Current Turbines, now owned by Siemens, who bought them out, I think it was last year, 2012. They've had a 300 kilowatt prototype installed off Lynmouth and Devon, called the Seaflow. It's done very successfully in terms of sea trials. It's now been decommissioned and sits outside of their offices down in Bristol. If anyone's interested, there's a news clip here of the working lunch, recorded some time ago now, but still very much apparent in terms of being able to witness and see the tidal flows and conditions. They've taken things a stage further and said, okay, we've gone from a single rotor of 11 metres diameter, let's go up to a much larger machine, enter the C-Gen installed in Strangford Lock, twin rotors, this time on a single arm, 16 metres in diameter, rated 1.2 megawatts. This is the installation. They had significant issues in terms of installing. It was due to go in 2007. Unfortunately, due to inclement weather, they were not able to install at that time. The necessary lifting equipment, as you can see, is very large. That was on contract to go elsewhere, essentially working in the oil and gas fields. So it was a complete year before they were able to reinstall the turbine, at which point they had a design change. Rather than rely on just a single monopile, to make the foundations easier, they split it out to this arrangement where they've actually got 4 smaller foundation structures to support the turbine rather than one large one, and it made installation for them far easier. Here's a picture of it undergoing maintenance. Maintenance of any tidal device is very important. Marine Current Turbines see their advantage as technically being that the blades are variable pitch, and the fact that they can twist them, so even if the water is flowing, they can pitch them to a 0 angle of attack, and therefore there's very little loading on it. They can then lift the whole framework on this arm out of the water, perform whatever the maintenance they need to do, in this case replacing of a blade, and lower it back down into the water again, all without requiring heavy lifting equipment or gear. They also see that the fact that the thing sticks out of the water is very good in terms of navigational purposes, warning other sea users of the presence of the turbine, and that it's therefore liked by the coast guards and other things. I should perhaps point out that in terms of being able to do this and install it at Strangford Lock in Northern Ireland, they've had to do a very detailed ecological report based on someone sat on the beach up to a year before the turbine went in, monitoring the seal population and how they're moving around. Since it's been installed, they've had people monitoring again, sat on the beach. Fortunately now they're allowed to sit in a control room and look at a radar display. However, if they're approaching from the radar to the turbine, they've got a big red button to press to say stop, just because no one wants to see a seal cut up as a result of this type of technology, and suddenly the technology gets put all over the media, killing seals. It would no longer be acceptable. I should point out that the rotational speed of the blades is about 10 revolutions per minute. They're very slow, and therefore most seals will be able to outperform them in terms of any manoeuvres and swimming anyway. It's not like a ship's propeller that's probably turning 10 times that. In terms of the future, Marine Current Turbines, they've got a couple of tidal farms planned, going for much larger machines, still based on the same C-Gen device of 2 rotors on a single arm. The first of those is at Anglesey of 10 megawatts by 10 devices, so 1.2. And then the slightly larger machines, 4 of them, 2 megawatts each, at Kyle Ree, also due, I think, before 2020 in terms of the installation. Looking further afield, we've also got some idea of their proposals of how they can go deeper offshore. So if you can't fasten things to the seabed, what could you do? Well, in this instance, there's a sort of floating pile arrangement. So you'd float it out to sea and then sink it down, or alternatively have this wing arrangement that would be attached to the seabed on a long arm, and similarly for maintenance, you just simply float the whole thing up out of the water, do your maintenance, float the whole thing back down. Tidal Generation Limited, acquired by Rolls-Royce, now been acquired by Alstom, are probably the second place. Slightly different in terms of the concept of how the device works. Still a horizontal axis in terms of the device, but the idea here is that the whole nacelle arrangement floats. In that respect, on the seabed, you put your foundation structure in place. You then float down using an underwater vehicle to secure it in place. It then produces energy. For any maintenance that's required, you simply release the nacelle from the foundation. It floats up to the surface again. You tow it back to the harbour where you do your maintenance before you tow it back again. Atlantis Resource, again horizontal axis. This time they have a fixed pitch blade. So rather than having variable pitch like marine current turbines, they have a fixed pitch arrangement, and they've gone for a twin rotor design initially, where one rotor takes the flow in one direction, and then the second rotor takes the flow in the opposite direction. So as the tide changes and comes in and out on the ebb and flow, they have a different rotor to take the power off each time. When they put it in the water, after a couple of weeks the blades broke. They weren't expecting the load that they got. Similarly, marine current turbines have had blades break. Open Hydro have had blades break. I think every manufacturer that's put a reasonable sized device in the water has had something break on it. Yeah, we're still learning. We're still trying to get it right. I think one of the messages that they've got from that is the twin rotor system isn't particularly reliable. They get a lot of fatigue occurring on the trailing rotor. So they're therefore looking now at single rotor devices similar to the Alstom device that we've just looked at. Taking that further, farm arrangements, Tidal Energy, they're looking at multiple pods all arranged around essentially a triangular framework system on the seabed. Again, that would stay in place and maintenance would be just lifting the pods on and off. In this case, they're all rotating in the same direction, whereas the CGen counter-rotates in opposing directions. But they're supposedly looking at off the coast of Wales, several sites in terms of development, and looking at the Welsh infrastructure and Welsh government in terms of co-funding for some of those projects. Open Hydro, slightly different in terms of the concept. Rather than work on a central shaft and have that rotate, you use the outer side of your rotor as your stator, and you can generate the electrical field from that rotating in terms of magnets. The middle of the turbine doesn't really move very fast anyway, so you don't get much power output from the centre of it. And they've had it installed at EMEC, the European Marine Energy Centre, up in Orkney. They're also preparing off the Irish coast. They're an Irish-based firm, so it makes sense for them to start there, as well as a number of units in the French coastline. Okay, so moving forwards with their designs. People often ask about shrouded turbines, knowing this relationship in terms of the water velocity flow rate. If you can increase the velocity, potentially you get significantly higher power capture. So the idea here is by using some sort of shroud around the turbine, you increase the flow through the turbine, that generates more power. So Lunar Energy are one of these concepts. In terms of maintenance here, we have a removable cell. So all the moving parts you take out and lift to the surface to do any maintenance. Everything else stays on the seabed in terms of the large shrouding. So again, it's reducing the craft size and requirements in terms of doing the regular maintenance. And although they had very good agreements and ideas back in 2010, there's nothing really new on their website. So I think they're struggling to find investment for their technology types. Slightly different in terms of the seabed mounting in this case. It's a gravity foundation, just a large lump of concrete to hold it down, rather than actually drilling into the sea floor or piling into the sea floor to hold devices in place. So those are the sort of main ideas in terms of what I would term horizontal or axial flow systems. Some variability around that is vertical turbines. Vertical axis turbines existed in wind technology for a number of years. Most now have been replaced by the horizontal axis system. That's not to say that they're not appropriate for use in tidal conditions. One of the big advantages that vertical axis systems has, that all potentially the generating equipment, everything that's electrical can be put on the water surface, making maintenance requirements significantly less. Okay, you don't have to submerge everything under the water because it's orientated vertically. It gives you a big advantage in that respect. Similarly, vertical devices, they can take flow from any particular direction. They don't have to be aligned with the flow, and in certain locations where you don't get repeatable conditions of the flow going out a different way from what it came in, a vertical axis system may offer significant advantages. I don't intend going through all those with you. So, work at Lancaster, just to finish with. I always ask for a picture, so there you go, there's a picture. It's not particularly meaningful, but I'm working on what we'd term multi-element high lift systems. Okay, and it's comparable to both vertical axis devices and horizontal axis devices. So what do I mean? Well, the inspiration really came in terms of Formula One racing, where they're pushing their technology, pushing their understanding to the limit, trying to get that extra tenth of a second off their lap time. And it all comes down to aerodynamics and giving the car downforce so it's got grip in the corners. And you can see in terms of the front wing arrangement on this McLaren, it doesn't consist of just a single wing, but the several wing elements all stacked together, all intended to improve the airflow over the vehicle, but also improve the downward flow of force to grip the car into the road. So if you can do it for a car and you do it for a plane on takeoff and landing, why can't you do it with a turbine? So the theory suggests this. If you have a plane wing form, you get a certain coefficient of lift at various angles of attack. If you then add a flap to it, you get a significant increase in that coefficient of lift. And if you put what's known as a leading edge slat, which is at the front of the airfoil, on top of that, you can get further lift still associated to it. So we know we can improve the lift. What we don't really know is, can we improve that lift without significantly increasing the drag that's acting on that turbine? Because in terms of turbine design, the critical point is having an appropriate ratio between the lift curve and the drag curve, or the lift to drag ratio. Optimize that, and typically you'll be optimizing the turbine. So we're looking at doing a similar thing by using multiple elements as to what we find in nature. The humpback whale here is far more manoeuvrable underwater than what it should be relative to the size of its geometry. People have looked at the fin arrangements and what we call the tubercles at the front leading edge of their fin, and it's that which distorts the flow around the fin, enabling the flow to stay attached to the fin for much longer, much steeper angles of attack, and therefore much better in terms of its performance. So we're looking at a man-made version of these by using multiple elements to keep the flow attached to the airfoil and improve the dynamic of it. So in terms of the research that we've looked at what we term a conventional flap system and a slotted flat system. One of the important differences between doing it in hydrodynamics compared to aerodynamics is the need to avoid cavitation. And cavitation is essentially where the localized pressure drops below a threshold that the water effectively boils underneath, and as that boiling, the air bubbles collapse, they cause significant structural damage to the structure. So we want to avoid that. So although we know the slotted arrangement is better in terms of overall performance, this peak here in terms of the lower pressure occurring is potentially damaging. Okay, so there's quite a lot involved with optimizing these systems so that we don't cause cavitation depending on the flow condition. In terms of the lift to drag ratio, can we improve lift and drag as a percentage? Yes, we can. You've got simulation results in terms of a standard aerofoil section with the blue line. By having a small flap and having the different deflection of that flap, you can see our lift to drag ratio increases from about 35 as a maximum up to about 45. So a significant proportional increase in terms of the performance potential of that as a turbine arrangement by using a flapped-based system. Put that all together onto a vertical axis turbine, and we get the following performance chart, where essentially the red or the blue represents the conventional turbine, the red where you're able to vary the angle of attack of that turbine blade by adding a trailing edge flap and varying the flap angle as well as the turbine blade angle. Potentially we can get out to that yellow line in terms of performance. With a vertical axis system, because you have in effect 2 bites at the cherry as the water passes the front of the turbine, and then again at the rear of the turbine, potentially you can get this effect. Similarly, looking at it in terms of horizontal axis turbines, we've also been doing some work, but it's very much at the early stages at this point in time, where we've modelled a simple split aerofoil section against a more conventional aerofoil section, where we do scale model testing in our tank at the university. And here we see the sort of performance characteristics. Typically turbines are defined by their tip speed ratio and the coefficient of performance. The performance coefficient is essentially how much you can extract from that body of water. There's a limit, supposedly the BETS limit of 59%, so we can't expect to get over 59% efficiency. Assumes an ideal expansion of the water. That is somewhat limited in the tides that you can have the seabed and the water surface, limiting that expansion. So theoretically, we could go beyond the 60% or 59% BETS limit in terms of energy extraction. So you can see here for the low speeds, we're certainly performing a lot better than the single blade, but perhaps for higher speeds, in terms of the water flow speed, it's not quite the same. Okay, and we think this is down just to the geometry, optimizing the angle of both blades relative to each other, optimizing it for a set flow condition should give a better performance overall in terms of the technology and technology type. I do have some samples of those blades here, which I can sort of pass around to you. It's a bit dark to see them, but essentially that's the one on the left-hand side, the single blade. That's the one on the right-hand side, the slotted blade, looking very much like a Formula 1 car in terms of the aerofoil section. So I've got a few of those I'll quickly send around.
You're nearly done, Steve.
Sorry?
You need a bit.
Yes. I think I've got one slide left.
Thank you.
So in terms of conclusions, I think tidal energy potentially offers a predictable form of renewable energy. It can compete in terms of cost. We do know the technical challenges that we face, but we are doing reasonably well at the moment in terms of tackling those and coming up with solutions to make economically viable. There has been significant growth in the sector. I think when I started, there was 2 or 3 devices. As said, now if you were to do a search, you'd probably find not far from 100 devices undergoing technical development, and therefore it's not clear as yet what the outright winner will be, whether it will be a horizontal axis device, whether it will be an oscillating device, whether it will be a vertical axis system. A lot will depend on the specific location that is to be installed and the local tidal conditions as to which technology type is going to be best suited. And similarly, I think in terms of the research work that we've done at Lancaster, that high lift solutions do offer potential gains for all these differing technology types. The UK does require a varied power distribution system and energy generation system in order to remain competitive.